All right, so the next configuration that we're going to talk about is a Y to delta. So the figure below shows a Y to delta configuration. As seen below, the load Z delta is connected in a triangle shape. So we jump down to here. So here we have our Y source. All right, and then we have our delta load right here. All right, so if you measure the line to line voltage, you will actually will be measuring the phase voltage of that respective load. So if you take a voltmeter, and you connect it right here, and you connect it right here, what you actually will be measuring is the phase voltage of this AB load right here. So this point will be connected right here, and this point right here will be connected right here. So what you'll be actually measuring is the phase voltage across ZAB. All right. So the same voltage formula still applies as in the Y to Y configuration. However, the line current and the phase current will have a different relationship. The load the load phase current is the current that flows through the actual load. And the line current is the current that flows from the source to the load. So the line current comes from the source, flows in this direction, and then it hits this junction point right here. Where some go this way, some goes this way, in this direction right here. And all this is happening all at the same time, where these line currents are displaced by 120 degrees. So you get this line current coming right here, hits this junction, some goes this way, and some goes this way. Same thing with the B line current. Some go this way, some go this way. But in order to calculate it, you just use these formulas down here. So if we wanted to calculate the line current and we knew what the phase current was, all we do is multiply the phase current by square root 3. And then the line current is going to lag the phase current by 30 degrees. So we'll want to subtract 30 degrees from the phase angle of that phase current. And then likewise for the line current for B and C, the other two phases. And likewise, we can manipulate this equation and solve for the phase current if we knew the line current. All right, by taking the line current, dividing it by square root 3, and adding 30 degrees to the phase. So the line current is always going to be more than the phase current by 73%, which is the square root of 3, or you can look at it as 1.73 times the phase current. All right. All right, so here's an example. Determine the following. If ZL, this impedance, equals 75 at an angle of 50 degrees. All right, so what is given is you have your line voltages, which in this case they specify that EAB is going to be your reference voltage because we made it equal to 0. So that's going to be your reference voltage. All right. And so given that EAB is 208 degrees at an angle of 0, we can displace the other two phases by 120 degrees to find the line voltage. The load phase voltage. Note in this configuration, the phase voltage of the load equals the line voltage since each phase load impedance is connected across the two phases. Therefore, the line voltage is equal to the phase voltage of the load. So if you put the voltage across the load, or each phase load, will equal the line voltage, just like we calculated up here. And what's going to be different is the load current and the line current. But we'll get to that in a minute. So right here it says the phase voltage of the source was given. An example is a line voltage. So therefore you have to convert that line voltage to a phase voltage. Recall that the relationship of a phase voltage to line voltage previously discussed. And so we're just going to use that same equation that we once used before with a Y to Y configuration to calculate the phase voltage of the source. And so recall, what's given in this particular example is the line voltage. We don't know what voltage is across the phase. I mean, each phase of the source. We know the voltage across two phases, which is called the line voltage. And so we can just use that equation that we did before whenever we calculate whenever we had the Y to Y configuration to solve for the phase voltage across the source. So recall we have the line voltage. We're going to divide it by the square root 3. And remember that the phase voltage lags the line voltage by 30 degrees. Which is why we're subtracting 30. All right, so the next is the load phase current. So we just use our Ohm's law to solve for the load phase current, because we already know the voltage across the load, which is VAB, divided by the load, which was given in the problem. And so we can just calculate the current respectively. And we should get the same magnitude for each phase current. The only thing that would be different is the angle, which is displaced by 120 degrees. And then to calculate the line current, you'll want to take that phase current, multiply it times the square root of 3. And the line current, in this case right here, is going to be lagging the phase current by 30 degrees. So you want to subtract 30. And so for this example, we get a line current of 4.8 at a phase angle of negative 80 amps. And we follow the same formula to calculate the other two phases line currents. All right, so here's a note for this configuration. The line current is equal to the phase current of the source. So in other words, what it's saying is the current that's flowing coming from the source is the same current that's flowing through the line. This right here is called a line. So this is a terminal right here. These are terminals. And so the current that's flowing through this source right here is the same current that's flowing through the line. But it's not the same current that's going to be flowing through the load because of this delta configuration.